Hello, welcome to this video. So in this video we're going to be talking about Hamilton's equations. Now Hamilton's equations are very useful classically and also provide a structure we can extend to quantum field theory. Hence they're in a chapter in a book about quantum field theory, and in this playlist where we go through the book, well at least the main contents, most of the main contents, where the book is called Quantum Field Theory for the Gifted Amateur, and provides the introduction for essentially non-postgraduate physics students to the field, although I'd like to embellish the discussion of these topics a little bit in this series. Like I will do in this video, where I'm bringing the idea of a chaotic system, which is a very good classical application of Hamilton's equations. So if we start with classically, Hamilton's equations are very useful because they introduce the idea of if we have a particle moving in physical space and we have some associated momentum of this particle, which we might call generalised momentum or more formally conjugate momentum. Hamilton's equations tell us how the state of this particle, so how its position and the momentum will change over time through linking these quantities with something called the Hamiltonian in a pair of differential equations which together are called Hamilton's equations. Now the Hamiltonian, as we will see, is essentially a description, at least for closed systems, of the total energy of the system. And because the total energy is conserved, Hamilton's equations also very neatly lead to a very fundamental way of describing conservation laws in classical physics. Also, Hamilton's equations, by thinking of evolution of a system in terms of the change of its generalised position and generalised momentum, allow us to visualise systems which are very sensitive to initial conditions, called chaotic systems. And chaotic systems appear a lot in nature. For example, if you have three stars, each with significant mass, and they're close to each other, then how they move in space will be dependent upon the gravitational interaction between all three stars. And this leads to a chaotic systems where if the stars start in even slightly different positions, then in the long term the stars will have very different motions in space. And this is important for working out whether a system of three stars is stable or when it's not stable, and therefore, for example, if there's enough time for planets to form between these stars. And so it has real applications in astrophysics, particularly because, well, systems with three stars are less common because they tend to be unstable. They do exist in nature, even though binary systems, the systems with two stars, are more common. But in terms of quantum field theory, Hamilton's equations are really useful because the connection between the position of a particle and its generalised momentum is very similar to the connection between a field, which describes, say, a particle, and its associated momentum, which we call canonical momentum. And by introducing an equation from quantum mechanics, a generalised form of Heisenberg's uncertainty principle, we can talk about how the field and its canonical momentum relate. And this leads to the idea of the field being quantised, and it's this quantisation that ends up predicting the existence of particles. So whilst in the last video we looked at quantising classical observables like the potential energy, leading to the idea of forces really being the exchange of force-carrying particles, it's actually Hamilton's equations, or the form they provide, that allow us to start to talk about how we get force-carrying particles in the first place, in terms of the quantizing fields. And similarly, you can apply this to matter particles. We'll see that a electron, for example, as a particle, is just the result of quantizing a quantum field which relates to the electron particle. And also how the fields interact and change over time is essentially a quantum field theory form of Hamilton's equations. And how the fields change over time is very significant because particles are simply the quantization of these fields. It's worth saying a lot of the time, the irony with particle physics is that it might sound like it's the study of particles, but really it's the study of quantum fields. But when you quantize these quantum fields, you generate particles from that, but particles are really just manifestations of these quantum fields being quantized. And we'll look at that in a future video, but that's why Hamilton's equations are important in a quantum field theory context. Although in this video we'll look at firstly the idea of generalized momentum associated with the position of a particle, then we'll introduce the Hamiltonian and then derive Hamilton's equations, relating it briefly to chaotic systems before we talk about how Hamilton's equations allow us to describe conservation laws at the very end of this video, and we'll relate that briefly to quantum mechanics. So that's where we're going, and I hope you learn a lot about classical physics and its connection to quantum stuff. So, yeah, let's get going with all this, wonderful maths, and we'll end in some very interesting places, I think. So, as mentioned, we need to get to some generalised form of momentum. Now, in terms of when we're considering momentum associated with a field, we do generally call it canonical momentum. However, when we're considering momentum associated with a particle, for some reason we don't use that term usually. We tend to use the word conjugate momentum, which I know is slightly confusing. I don't know why we can't have the same word for both. But conjugate momentum is just the generalised position of it's just a generalised momentum of a particle. But you might ask, well, what is generalised momentum? Well, we can describe the position of a particle in space in many ways. For example, if we have a Cartesian coordinate system with our x, y and z axes, and we consider the motion of a particle in that Cartesian coordinate system, then one thing the Cartesian coordinate system is very good at describing, much better than things like polar coordinate systems, are straight lines. The expression of a straight line in terms of Cartesian coordinates is very, very straightforward. In fact, it's for that reason why in school you tend to use Cartesian coordinate systems, because they are excellent at describing straight lines. Also things like quadratics, which are also very useful. But if we think about a straight line and a particle moving on a straight line, then there's a particular kind of momentum, if you like, a measurable quantity of how hard it is to stop the particle associated with its motion in a straight line. And we call that kind of momentum linear momentum. But we can think of another way of describing the position of a particle in space that would have a different natural kind of momentum associated with it. So if we've got the Earth orbiting the Sun, because it's orbiting, we would naturally describe where it is in terms of its angular position. We could imagine how many degrees or radians it has moved, since a month ago or something. And so we're considering changes in angular position. And providing we approximate the Earth's orbit as being very circular, then that makes perfect sense that we would only really care about angular position. And we can ask, well, what kind of momentum is naturally associated with, if you like, angular coordinates? Well, the Earth, when it's orbiting, is, well, orbiting, so the natural type of momentum to consider is a type of momentum called angular momentum. Angular momentum is also a natural candidate to consider as the natural momentum associated with something spinning, which is again to do with changing angular positions. So for a particular kind of set of coordinates in space describing fully where something is in space, there is a natural kind of momentum associated with it. And we can actually generalise this, and we can go, well, okay, if we have a generalised coordinate system, generalised form position, then how does that relate to a kind of generalised momentum associated with that? In other words, how does generalised position relate to conjugate momentum? And how they relate is governed by Hamilton's equations. But to get to Hamilton's equations, we need an expression for, firstly, the Hamiltonian, and also for conjugate momentum. And to get there, we need to consider the time derivative of the Lagrangian. Now, the Lagrangian formalism of classical mechanics is one that predicts the trajectory of a particle, although we can generalise it to a field, as we will do later in the series. But if we're considering a particle, then essentially the Lagrangian formalism goes, well, the particle will follow a path that minimises a quantity called the action. And the action is, if you like, the sum of the Lagrangian. It's like the integral over the Lagrangian over time. So the Lagrangian formalism is kind of neat because it relates the idea of a trajectory to minimising, to at least having a stationary version, so usually minimising a particular quantity. It could also be maximising a quantity, but the key thing is we have a stationary action. And that allows us to actually connect particle mechanics to things like optics, which helps us talk about wave-particle duality. So it actually goes quite deep. But the Lagrangian itself is the difference between kinetic and potential energy. And so if we could consider the time derivative of the Lagrangian, we need to think of what the Lagrangian depends on. So the Lagrangian, being the difference in kinetic and potential energy, generally depends on position, which in its generalised form has the symbol Q. If we're talking about a particular position coordinate, let's say the ith position coordinate, we say Qi, with I being the subscript. And the Lagrangian will also depend on Qi dot, because kinetic energy, which the Lagrangian partially depends on, relates to how quickly something's moving, so will depend on Qi dot, whereas the potential function does generally care about the separation between particles, and so will depend on Qi. And for some forces, like the Lorentz force, which describes how a particle moves in a magnetic field if the particle is charged, then the potential might also depend on Qi dot as well as Qi. But the main thing is, for essentially all of standard physics, the Lagrangians just depend on Qi and Qi dot. We don't have to consider any further time derivatives. We're saying Qi dot is just the time derivative of Qi. It's how quickly Qi changes, or if you like, generalised. Qi dot is essentially generalised velocity. So, because the Lagrangian depends on kinetic and potential energy, and kinetic and potential energy together depend almost exclusively on Qi and Qi dot, we can say that the Lagrangian itself depends on Qi and Qi dot. And therefore, using this, we can use the chain rule to write a generic expression for the Lagrangian, knowing nothing more than simply it is a function of Qi and Qi dot. And the time derivative for the Lagrangian we get is given here. This is justified by the chain rule, and this is true no matter what the Lagrangian is, providing it is a function of Qi and Qi dot. And to get this, as I say, you use something called the chain rule. Now, if we want to simplify this, and we will want to simplify this to introduce the idea of conjugate momentum and Hamiltonian, we can do that by combining the two terms we have, one which depends on Qi dot and the other depends on Qi double dot, so if you like generalized acceleration, into a single term. Now, to do this, there's at first seemingly a bit of a problem. The main problem is that one of our terms is a partial derivative with respect to generalized position. The other one is a term that involves a partial derivative with respect to generalized velocity. Now, to combine them, we would like either both to refer to partial derivative with respect to generalized position, or both to refer to generalized velocity. And so we have to change one of the terms, or one of the partial derivatives, but we can do that using something called the Euler-Lagrange equation. Now, the Euler-Lagrange equation is essentially the version of the idea that a particle would like to have a stationary action for its trajectory, but under the assumption that the Lagrangian depends on Qi and Qi dot. That idea actually simplifies to something called the Euler-Lagrange equations. Now, I've done a video on the Euler-Lagrange equation, but for a summary, the Euler-Lagrange equation, as you'll find on the my previous video, and also as you'll find on many documents on the web and in many books, in any advanced book on classical mechanics, I have the Euler-Lagrange equation. And the Euler-Lagrange equation says, well, the partial derivative with respect to time of the partial derivative of the Lagrangian with respect to Qi dot is equal to the partial derivative of the Lagrangian with respect to Q. In other words, Qi. So in other words, the Euler-Lagrange equation relates how quickly the Lagrangian varies with respect to generalized velocity to how much the Lagrangian changes with respect to generalized position, and therefore it allows us to go between generalized position and generalized velocity very neatly. And so doing that, we can now actually alter the first of our two terms on the right hand side of this equals into a partial derivative of the Lagrangian with respect to Qi dot instead of Qi. And then we can combine the two terms together. And when we do that, we end up with this expression. Now, this expression I haven't derived fully because this video is not about the Euler-Lagrange equation or Lagrangian mechanics, it's about the Hamiltonian. And I've given all the bits of information needed to actually derive this kind of equation, so I think it's fun to leave it as a mathematical exercise. The main point is that this equation tells us that there's something special about this seemingly bulky and not very coherent term that we have in our brackets. There's something special about this because it tells us how quickly the Lagrangian changes with time, and it's the Lagrangian through the action, or in other words, the Lagrangian through the Euler-Lagrange equations, which determines the trajectory of the particle. So this bit in brackets is very crucial to the motion of a particle, and in the next slide we investigate what this bit in brackets really is. and that will lead us on to the idea of the Hamilton and conjugate momentum. So, as we mentioned before, the time derivative of the Lagrangian is in terms of this expression, which involves this slightly magical quantity in brackets, and we're going to investigate what this magical quantity is in this slide. So, for this, we're going to kind of define the Hamiltonian. Now, where you see three horizontal lines placed on top of each other, that's kind of saying that something is identically equal, which in non-technical jargon just means we're defining something to be this. So it's not, we haven't derived it to be true, we're just going, well, we could define a quantity as this expression. So we define the Hamiltonian, which has the symbol H, to be generalized momentum times generalized velocity minus the Lagrangian, where generalized momentum is also defined to be, generalized momentum is defined, so it's not just equal, it's defined to be the partial derivative of the Lagrangian with respect to generalized velocity. So it's how much the Lagrangian depends, if you like, on the velocity of the particle. And we might think that momentum should be associated with velocity, because at least in linear momentum, clearly how quickly something is moving will be the crucial thing that the linear momentum depends on. And you can extend this idea to other types of position and their associated conjugate momentum. Now, here, this is a very abstract definition of the generalized momentum and the Hamiltonian, so let's explore what this actually means in practice. Well, if we look at the equation we have at the top, then using our definitions for the Hamiltonian in terms of the conjugate momentum and how the conjugate momentum relates to the Lagrangian, we can actually rewrite the top expression as simply the statement that the rate of change of the Hamiltonian with respect to time is zero. So in other words, we've gone for any system where the Lagrangian is a function of generalized position and generalized velocity, which is the vast majority of classical systems. At least closed classical systems, the rate of change of the Hamiltonian is zero. So the Hamiltonian is some kind of constant of motion. And you might wonder, well, what is this constant of motion? Well, as we said, the Lagrangian is the difference in kinetic and potential energy. And also, if we think classically of usual coordinates, well, momentum is just mass times velocity, and well, generalized velocity would just be velocity. So in terms of usual coordinates, generalized momentum times generalized velocity is just going to be mass times velocity squared, which is twice the kinetic energy of a particle. And so the first bit in our definition of the Hamiltonian is just equal to twice the kinetic energy of a particle, and to get the Hamiltonian we have to take away the Lagrangian from this. Well, if we take away the Lagrangian from twice the kinetic energy, then we're going to end up with saying that the Hamiltonian is the sum of the kinetic and potential energy. So in other words, the Hamiltonian is the total energy of the system, or if we're doing thermal physics, kind of like the internal energy of the system. It is essentially the total energy present in the system. And so the meaning of dH by dt is zero is that in a closed system, energy is conserved. The sum of kinetic and potential energy will be constant. So the Hamiltonian, if we're considering a closed system with traditional forces, can be thought of as the total energy of a system and is therefore naturally conserved thanks to the conservation of energy. So that's the meaning of the Hamiltonian. And we can also see through this kind of slide that generalised momentum does act like momentum, and generalised velocity does act like velocity, and it all fits together to allow the total energy of a system to be conserved. Now in the next slide we're going to be moving on to Hamilton's equations. Now that we've defined the Hamiltonian and also our conjugate momentum, and that will lead us on neatly to a brief discussion in this video at least, of chaos physics. Hello, so in this video, in this last bit of the video, we'll be looking at Hamilton's equations. So on the previous slide we defined the Hamiltonian and we also defined the conjugate momentum. And here are our definitions. And now we'll derive a pair of differential equations which together are called Hamilton's equations. One concerns how the Hamiltonian varies with generalised position, the other concerns how it varies with conjugate momentum. So if we look at the first of these equations, the Hamiltonian we defined it in our kind of top equation, and if we look at how it varies with generalised position, if we look at how it varies with generalised momentum, well, we can just read it from the top equation. So the first term in the Hamiltonian will just leave us, when we look at the partial derivative, with just qi dot, so generalised velocity. Now the second term is going to depend on how the Lagrangian varies with generalised momentum or conjugate momentum. But we've assumed that the Lagrangian is a function of q, and q dot only is not a function of generalised momentum, and therefore the partial derivative of L with respect to generalised momentum will be 0. And therefore all we're left as our first equation with the partial derivative of the Hamiltonian with respect to conjugate momentum is just generalised velocity. Now the second equation is more subtle, so if we consider how the Hamiltonian varies with generalised position, well, now the first term doesn't give us anything in our expression for the Hamiltonian. So the derivative we're looking for is just minus the derivative of the Lagrangian with respect to generalised position. Now using how we defined the conjugate momentum, we can rewrite the Euler-Lagrange equations as the partial derivative of the Lagrangian with respect to generalised momentum. We can rewrite the Euler-Lagrange equations as the partial derivative of the Lagrangian with respect to generalised position is just the time derivative of the conjugate momentum. That's just another way of writing Euler-Lagrange equations, and this leaves us with our expression here. Now, these two equations together, these two equations in our blue boxes, form Hamilton's equations, and the beautiful thing about them is they get to the heart of the physics of how systems evolve classically. Because if we think of a classical system, if you know the position of a particle and say its momentum, then it's kind of natural to think, well, you'll know how the particle will move, or you'll be able to create a prediction for how it will move going forwards in time. And indeed, the state of a system is described by position and conjugate momentum fully, at least for a closed system in classical mechanics. So it's natural to think how position and conjugate momentum evolve. And also these equations seek a description for how they evolve, but they allow for the possibility of the time derivative of Q to depend, say, on, for example, to depend on conjugate momentum, depending on the form the Hamiltonian takes. And therefore these equations permit the time derivative of position, or generalised position, and also the time derivative of conjugate momentum to depend upon conjugate momentum and generalised position. Meaning they don't require us to end up with a situation where we're seeking, as we would in Newton's laws, to find an expression for how the generalised position varies with time as a function of time. And it's because Newton's laws tried to do this very strange thing, which doesn't relate really fully to the state of a system or consider how the important parts of the state of the system, the generalised position and conjugate momentum, evolve, which makes Newton's laws very difficult to apply to systems which are very sensitive in terms of how they evolve based on their initial state. And so that's one reason why Hamilton's equations are much better than Newton's laws if we're considering chaotic systems. They get to the heart, or rather they describe the physics in terms of things which are a much more natural description. And when we're talking about the motion, we're describing the motion in something called phase space. And phase space is essentially a space where one axis is the generalised position and the other axis is the conjugate momentum. And our system evolves is just tracked by seeing how these quantities vary with each other. So you can talk about the evolution of a system as a trajectory on phase space. So to summarise where we've been before we see an example of a chaotic system, well, a mathematical example at least, we're going to briefly review the road we've been on in classical physics. So you're familiar with Newton physics from probably school or university, where you're describing things in terms of forces. The Lagrangian formalism comes along, gets rid of the idea of forces, replaces it with the idea of potential energy, and then the Hamiltonian formalism comes along and uses the Lagrangian setup to describe the evolution of a state of system very naturally in terms of the Hamiltonian, the total energy of the system, and is beautiful for chaotic systems. And now we're going to move on to seeing the mathematical example of a chaotic system. So here's a mathematical example, and you can see that there are regions in the phase space where a slight change in the initial position will result in different trajectories in phase space corresponding to different evolutions of the system. So this is a chaotic system, at least in some regions of the phase space. And associated with this is the potential we have at the top, which is the potential which is governing this chaotic system. And the potential here is the symbol U, which in classical physics you use U, in quantum mechanics you use V for potential, but it's the same thing. And this potential is a function of generalised position, like most potentials in nature. And we see that there's a region in this potential which is allowing kind of orbits, if you like, in phase space, so some stability of the evolution of the system, where it will return back to the original state. And that's caused by the fact that this potential on the left-hand side of the graph of the potential has a minimum. That is, there is a lower bound, and to lower the energy, a system or a particle will always try to get to the minimum potential, so it lowers its total energy, or the Hamiltonian. and therefore a system will have some kind of repeated periodic nature in terms of its state. It will always kind of loop back to the same kind of state if there's this minimum potential. However, if there's not this minimum potential, like we can see on the far right hand side of both diagrams, then the particle will keep trying to get to a lower and lower potential, but because there's no minimum potential, it will never end up really at the same state it really began at, and so we don't get this kind of stability in the phase space. And we can also see from the diagram the more extreme the rate of change of the potential. So classically, the stronger the force, the more significant the chaotic nature or sensitivity of the system becomes. Now, I will, in a video later, probably the one after this, talk about the maths in detail of a pendulum, because when a pendulum has a lot of energy, it's an example of a chaotic system. But I'll leave the general discussion of chaotic systems here and now move on to conservation laws and relating that to Hamilton's equations through something called the Poisson bracket, and then we'll link it with quantum mechanics and the idea of a commutator at the very end of this video. So we mentioned that there's a connection really between position and conjugate momentum, and therefore Hamilton's equations, between classical physics and quantum field theory. Now we're going to look at another connection, and this connection, well, this is really more a connection, I suppose, between Hamilton's equations and quantum mechanics. And this is about the idea of conservation laws. And in quantum mechanics, you get an observable is, as much as it can be in quantum mechanics, conserved if it commutes with the Hamiltonian being an operator that represents the total energy of the system. Well, we have a classical version of the Hamiltonian. It's not an operator, it's a function, because this is classical physics. And the Hamiltonian represents the total energy of the system. So you might think that, well, there must be some, if not commutator, but some operation involving our Hamiltonian here and an observable, another observable, which would mean, well, if the Hamiltonian is conserved, as we've shown it is for the closed system before, then so will this other observable be. And we can indeed get that, but in classical physics, the relationship isn't given by a commutator, it's given by something called a Poisson bracket. And it works thanks to Hamilton's equations, as we will see. But we firstly have to define a Poisson bracket. Now, the mathematical definition of a Poisson bracket doesn't really have any physical meaning because it is a mathematical definition. Having said that, I'm sure mathematicians have come up with some rather abstract general meaning for a Poisson bracket in its mathematical sense. But we'll be really interested in its meaning in terms of the context of Hamilton's equations, because we're saying generically the definition of a Poisson bracket to get us going. So it's this rather confusing thing. Now, for a Poisson bracket, I put curly arrows like here, and then a P as a subscript to remind me that this is a Poisson bracket, not an anti-commutator, because anti-commutator is something that comes up a lot in quantum field theory, but putting a P as a subscript just reminds me this is a Poisson bracket. There's no real standard convention apart from a Poisson bracket always involves these sets of brackets. And usually in the context of physics at least, where there is possible confusion with other things, there's something indicating it's a Poisson bracket. But this gives us a Poisson bracket for quantities A and B. Now A and B relate to something about the state of the system, so it could be energy, it could be position, it could be velocity, you There might be functions, things like the potential, energy, but A and B are some quantities, and we define for any two quantities A and B that their Poisson bracket is given us here, where you'll notice that the Poisson bracket makes explicit reference to generalised position and associated conjugate momentum. And so, to make physical sense of this, we bring in something that involves generalised position and conjugate momentum, that is Hamilton's equations. And, well, we'll do that in a sec. I'm getting slightly ahead of myself. But to see how the Poisson bracket works so far as showing considered quantity, so we want to express a Poisson bracket using ideas in Hamilton's equations, but we also want to see generically, if we have a function, how will it vary with time. Well, just as we did with the Lagrangian at the start of the video, where we looked at what dl by dt was before introducing Euler-Lagrange equation, and we can do a similar thing with our function, which will be a description of some physical quantity, which we'll call f. And we suppose that this physical quantity is going to be some function of position, conjugate momentum, and time. So I suppose, and you might think, well, you can't really do that because kinetic energy, for example, isn't going to be a function of these things because it's a function of generalised velocity. But it's worth saying kinetic energy can also be thought of as a function of conjugate momentum. So that would still be a candidate for our function f. So we can actually describe a lot of observables in terms of f. And as we've seen with phase space, all we really need to work out the evolution of a system, so how it will change with time, is its current position and conjugate momentum, even in the case of chaotic systems. And adding time in is just always good, because you never know, a function might explicitly depend on time, like say you've got a time-dependent force or something. Well, generically the derivative of f with respect to time will be given by this, and this is true by definition. This is just assuming f is a function of position, conjugate momentum, and time. Very similar to what we did with the derivative of time for the Lagrangian before. Although for this we include the possibility of time because we're thinking of conservation, of course, so we want time to be a possible thing that f could depend on. And so now we use Hamilton's equations. And by using Hamilton's equations, we can actually, because Hamilton's equations give us expressions for q dot and p dot in terms of how the Hamiltonian varies with generalised position and also conjugate momentum, we can rewrite the time derivative of f in terms of derivatives of the Hamiltonian, and when we do that and also make use of our Poisson bracket, we can see that df by dt has a form where the last two terms in the last two terms in df by dt actually can be written as a Poisson bracket between f and the Hamiltonian. Now I leave that as an exercise to the viewer if you're interested to do. This is just a general light overview, so there aren't any derivations, but I do like to give all the information needed to derive things. And if you do that, you'll end up with this lovely expression for the time derivative of a force. And what this says is the time derivative of a force is equal to the partial derivative of f with regards to time. So in other words, how quickly f explicitly depends upon time, plus a Poisson bracket between f and the Hamiltonian. And what this implies is if f doesn't explicitly depend upon time, then df by dt is equal to the Poisson bracket between f and h. Therefore, if f is a conserved quantity, so if df by dt is 0, then our Poisson bracket will also be 0. So we have a link between conservation and Poisson bracket that is very similar to the link between Poisson bracket, which is very similar to the link between commutators and conservation laws in quantum mechanics. And we'll talk more about that link on the next slide. So as we said, there is a link really between Poisson brackets and conservation rules, and also a link between the quantum commutator and conservation rules. And we can explore this link in this slide. Now, it's worth saying the link involving the quantum commutator, I will write a simplified mathematical equation for. The more full mathematical equation summarises something called Ehrenfest theorem, if I'm pronouncing the name right, and really you can use it to do all kinds of things because of kind of its connection with conservation laws, and also the fact that classical physics clearly has a very similar relationship with conservation laws. And you can actually use Ehrenfest theorem to show that Schrodinger's equation ultimately would result in Newton's laws for a macroscopic object on the appropriate scales. But anyway, here is a very light overview with admittedly some simplifications for the quantum commutator. So, the time derivative of f time derivative of f, as we said, is equal to the partial derivative of f with respect to time plus the Poisson bracket with respect to f and the Hamiltonian. And if f doesn't depend explicitly on time, then the derivative of f with respect to time is given exactly by the Poisson bracket. And so if essentially the Poisson bracket is 0, then f would be a conserved quantity. Similarly, in quantum mechanics, if we think of an operator A, then simplifying things a bit, we can say, well, if A is kind of conserved and A doesn't explicitly depend upon time, then the commutator between A and the Hamiltonian will be 0, albeit with A and the Hamiltonian being operators in quantum mechanics, not functions. And it's worth saying here I have simplified things a bit, because really I should be talking about the expectation value of A, not A itself, because due to Heisenberg's acidity principle there will be generically fluctuations in A, albeit they might be really, really small compared to the values we might measure for observable A on a macroscopic scale. And so this kind of relation that we can see between conservation laws and the quantum commutator and also conservation laws and the Poisson bracket gives us a nice roadmap from classical to quantum physics. So if you want to go from classical theory and make it quantum, you essentially, to summarise very broadly, you replace the physical observables in classical physics with operators. You also replace the Poisson bracket that describes the conservation of quantities with a commutator, which will also describe the conservation of quantities. And it's important to have a roadmap in terms of conservation laws, as well as just how we're describing observables, or conservation laws are as important in quantum mechanics as they are in classical physics. Albeit in quantum mechanics it's a slightly bit more complicated because of Heisenberg's acidity principle. But that is a good general pattern. So in this video we've explored what the Hamiltonian is, we've looked at what conjugate momentum is, we've looked at using them to describe very neatly chaotic system and had a glimpse at what a chaotic system looks like in phase space, And now we've seen that Hamilton's equations, as well as being really useful for chaotic systems and very sensitive systems, of which there are many in the physical universe, Hamilton's equations also allow for a roadmap in terms of a Poisson bracket for us to jump between classical physics and quantum physics, because the Poisson bracket, with respect to the Hamiltonian, if we consider Hamilton's equations, define, essentially allow us to predict, if you like, whether a quantity we concern in classical physics, and we can use a very similar idea in quantum mechanics, all with very subtle amendments. So I hope you like this video. This video has been rather long. I keep meaning to make them below 30 minutes, but there is so much content to explore. The next video on this playlist will be a lot shorter, because it'll be just looking at a particular example of chaotic systems where I presume we're familiar with Hamilton's equations. But if you forget, this video will always be available on YouTube, at least for a very long time, probably forever. Probably even longer than I am on the Earth, although I don't know if YouTube ends up deleting them after 100 years or something. But in the next video on this series, we will look at chaotic systems in more detail, taking a bit of a detour from the book, and then we'll jump back in the video after that to keep on going with the book, where we'll look at the Klein-Gordon equation, which is one of the first equations to unify quantum mechanics and relativity, and did allow us to work out some very important features of, what today are known as spin zero force carrying particles. Admittedly, many force carrying particles do have spin, albeit integer spin, so spin zero is a bit of a simplification, but it's a good enough simplification that you can use it to understand some very useful properties of force carrying particles, and we'll look at that in a couple of videos time. So thank you very much for watching, and hope to see you in another video soon.